Okay. Hi, everyone. I'm Sherif Abbas at the Exciting Science Center of Excellence. Today, we're going to be going over one of the really cool DFT codes out there. It's an open source software. It's called GPAW. It's written in Python, and that's why I said it's cool, because not just that it's written in Python, you can use GPAW by writing in Python. Again, why am I still calling it cool? I mean, it's Python. What makes it different from other, coding programming languages? Well, GPO is in Python versus all of the traditional DFT packages that are written in traditional, programming language, such as Fortran, for example, which most of the DFT packages are written in Fortran. Fortran is very old. It's very well geared for for writing parallel high performance computing code, but not as many people now know Fortran as many, as much as Python. More people now know Python. Python is easier to learn, easier to code. So having DFT written in an easy to learn language is always a cool thing in my point of view. Okay, so today we're gonna learn how to use GPO, just the very basics of GPO for very basic DFT tasks. You can always take this and go forward and do other stuff with it. There's plenty of documentation about GPO on the GPO website. So what we will be doing today is just introducing what GPO is, how to set up GPO on your computer. That's the other part of coolness in GPO, is that you can actually set it up on your own computer easily. It's just going to be like 2 lines of code. 2 lines in the command line or the terminal. Which compared to, for example, setting up VASP, for example, or Siesta or Octopus on your computer, which is much more difficult or much more time-consuming. GPO is much easier to set up. And then bird's eye view of a GPO calculation, just from above, how a GPO calculation, like the workflow of a GPO calculation, sorry, how it looks like, setting up a calculation. And then we're going to be doing, for our basic GPO DFT calculations, we'll be doing a few examples, 3 examples in this tutorial. First example is the atomization energy of H2. We will calculate that, and then the structure of CO2. And then we will, so these are all molecular systems. And then we will go into some detail about periodic boundary conditions for supercell systems. And then we'll discuss just let's say a little detour into the exchange correlation and how it's, what it means for people new to DFT, and how to handle it in GPO. And then we will do a surface calculation, the absorption energy of H on platinum. It's going to be a very simple, rough calculation. It's not going to be delivering accurate results, that one, because to do accurate surface calculations for metals in particular, in GPO, one needs certain parameters to be, to have let's say the systems to be a bit larger. I'm going to discuss this in more detail as soon as we get there. But I'll be showing you the main features of using GPO for absorption energy calculations and establishing supercells or slabs, for any surface calculations. Okay, let's start. What is GPO? GPO is a DFT software, as I said. It's written in Python. You can build systems in GPO using ASE. So actually, GPO is based on ASE, and ASE is an amazingly large and diverse and versatile Python environment. It's called the Atomistic Simulation Environment that helps. It's a helper. Let's say it's a DFT helper code that helps you build systems and run simulations. It doesn't really do DFT itself. It uses other DFT codes to run DFT, such as GPAW. So we've got GPAW and ASE. What sort of DFT calculations or atomistic calculations that GPAW can do? A large number. It's really rich with all sort of things that you can do, with DFT, like standard DFT, time-dependent DFT, quantum transport calculations as well, ab initio, molecular dynamics as in classical molecular dynamics, quasi-particles, BSE, and it also has a lot of post-processing features, such as calculating the band structure and a lot of density of states and a lot of other things. So that's, GPAW. It's also heavily documented online. So whenever you want to go and learn more about GPAW, it's all there. And also a lot of tutorials. So one thing to also remember about GPAW, I think it's written by physicists. So, and physicists, the units of measurements that physicists always favor for energy is the EV, as compared to the unit of measurement that chemists like to use, the kilomole. All energies in GPAW are in AV, and all lengths are in angstroms. Okay. So if you want to set up GPAW on your own computer, then those two lines. First, you go Python 3 -m pip install GPAW, or just pip 3 install GPAW, which is this line here. And then once you have GPAW installed, you need to install the PAW, or the pseudo-potential files for all the atoms. GPAW is a DFT package, so it represents each atom using a pseudo-potential. So if you want to do DFT calculations, then you want to download all of those data files into a folder. And so first you create a folder, MyPaw, for example, whatever you want, and then inside that folder you type this command, and this is going to set up that data file to be used by your own GPAW that you have installed here. And that's it. Actually, you're ready to start using GPAW. So as I said, a bird's eye view of a GPAW calculations from above. GPAW uses ASE, as I said. So in GPAW, the workflow goes like this. First, you establish your system. You create your molecule, your supercell, your surface or whatever, using atoms, the atoms class. Atoms class is part of ASE, as I said, which is the helper code for DFT calculations. By the way, ASE can help GPAW. It also helps almost every other DFT software, a lot of other DFT software such as VASP and Siesta and Quantum Espresso. So once you've established your system with the, using the atoms class from ASE, then the next step is to set up the DFT calculation using the GPAW class. Once you're done with that, you make a few function calls to actually start the DFT calculation. For example, let's calculate the, let's create a system with only a hydrogen atom. So we're going to place a H atom at the center of a box of size 10 by 10 by 10. Okay, so the center of that box is going to be 5 by 5 by 5, right? So to do this, we create a new atoms class, just the normal way of creating a new object based on a class in Python. So you would go atom, or you can call this just a variable, equals atoms, which is the atoms class. And then the first parameter is H here, which is the atom itself that you want to place. And then you pass those two parameters. Positions here is where you want to situate each of the atoms that you have passed here. And so it has to be a list of lists, right? It's a list of lists. Each one of the inner lists has 3 numbers, the X and the Y and the Z. So you've got 5 along the X-axis, Y-axis, and the Z-axis. And it's only one item or one element inside that bigger list, right? Because we only have one H atom. And then the cell equals, and these are the dimensions of the cell, which is assumed as by default to be cubic cell. Okay, let's say you want to place a H2 molecule. And you want to, so the H2 molecule, the distance between the two H atoms is around 0.7 angstroms. So we're going to put one H at 5 minus 0.35 and the other H 5 plus 0.35. Remember, the center is 5, 5, 5. So we're going to place one here and one there. So one is 5 minus 0.35 and the other is 5 plus 0.35. Note positions here is actually a tuple of two lists, right? So here is one list of numbers and here is another list of numbers. You can also notice that it's pretty flexible in terms of whether you use tuples or lists. Here I'm using a list of tuples, here I'm using a tuple of lists. It doesn't really make a difference. So the other thing is we need cell equals 10, 10, 10, and that's the supercell size. Okay, so here we created a H atom here in a cell, and here we created a H2 molecule in a cell. Now, the next thing is we are going to calculate the, do some basic DFT calculations for these, for hydrogen, the atomization energy for hydrogen. And I'm gonna now share code here. Now, the codes that I'm gonna be sharing in this tutorial are all available in the link. I think it's been shared in the chat. So you can just go there, and there are three Python code files there, and these are the ones that I'm going to be going through in this tutorial. So let's see how we can how we can actually make use of those codes. The first thing when you want to use GPAW, first thing when you want to use GPAW is first import atoms class. As I said, the atoms from ASE, and from GPAW install the GPAW class. Those two are the main two classes that we're going to be using. So what I'm going to do actually, I hope that the font here is clear to you. I'm going to start the terminal as well. IPython. So I'm starting the IPython 3 interpreter so that I'm going to be typing the code straight into the interpreter to show you how things work. Just takes a second, 2 seconds. There you go. So the first thing is copy paste that. So I'm importing atoms and I'm importing GPAW. Okay, it's doing the importing. Next thing is atoms equal atoms, H positions 555. That's the first example we had. It's a bit slow here. What's going on? Come on, man. Yep. So atoms equals atoms and so on. So now I created the atoms object and placed it in the atoms variable. Okay. Now that's just for placing H atom. What about placing two H atoms? Here you go. So this code, I place two H atoms as a H molecule in the supercell. And here I'm just showing you that it can be a list of tuples for people who know Python, list of tuples, and could also be a list of lists. It doesn't make a difference. Okay, now the atoms class comes with a lot of methods that can give a lot of information about the system that you've just created, such as, for example, get positions. It gives you the atomic positions that you have just entered. 4.65 and 5.35. 4.65 is just 5 minus 0.35. So this is an array of, or a NumPy array of the atomic positions that you have in a system. What about the chemical symbols? So atoms that get chemical symbols, and you've got H and H, of course. It's just a list of the atoms. Get distance. And get distance needs two numbers, the index of two atoms, indices of two atoms, and it's going to give you the distance between those two atoms. And obviously here 0.7. That's what we decided the atoms to be apart. And then initial charges. So the initial charges on those two H atoms are zeros. We didn't add any charge in the system. Initial magnetic moments, get masses, for example. So these are the masses of the atoms, and get PBC. PBC here is periodic boundary condition. What is the periodic boundary conditions in the system? I'm going to be talking a bit more about that in a few minutes, but let's just get what the settings are now. We didn't set any periodic boundary conditions. It's just a molecule, and therefore false, false, false. So false along the x-axis, false along the y-axis, false along the z-axis. So the system is not periodic in any axis. Get volume, it's going to be 1000 because we said 10, 10, 10. And then get cell lengths and angles, it's going to be 10, 10, 10, 90, 90, 90. 10, 10, 10, 90, 90, 90. Okay. We've been entering numbers like 0.35 and 5 minus 0.35. It would be cooler if we basically use variables. It will be more compact actually. So if I put A equals 10, D equals 0.74, which should be the correct distance between the two H atoms in a H2 molecule, and we just put positions equal A divided by 2, like 5, minus D divided by 2, which is half the distance between the two atoms, and then we copy paste that. So here we have created a H molecule in the system with a distance of 0.74 angstroms. Okay, now let's do the atomization energy calculation. And to get the atomization energy, we need to do two separate DFT calculations. One DFT calculation to calculate the total energy of the individual H atom. The other DFT calculation to calculate the total energy for a H2 molecule. Once you have the H2 molecule and a single H atom, then you can find out how you can get the atomization energy, which is the energy or the cost of splitting a H2 molecule into two H atoms. How much energy is needed? Just to get an idea, what we need to do is subtract from the H2 molecule 2 times the energy of the H atom. And this gives you the energy of splitting the H2 molecule. And we will be doing these calculations now. So first thing is we need to calculate the total energy for a single H atom. So this is the H atom in the atoms class, positions and cell like we did before. Let's just copy paste that. Now, we've been using atoms. Now we're going to be using GPAW, the GPAW class. The GPAW class, that's where the calculations are. So the first thing is we need to create the GPAW class. And the second thing, we need to set that this calculation object, which is an instance of the GPAW class, a reference to a GPAW object, is the manager or is the driver of DFT calculations for that H atoms object. So to do that, we set h.setCalculator calc here being GPAW. So we do this here. Next thing is, now that we have the system, the ASE atoms object, which is H here, the variable name is H, and the calculation object, which is calc. The next thing is we can just call get potential energy. So when I call get potential energy, it will actually do a single point DFT calculation in order to obtain the total energy. So here I'm going to be doing this. Now, actually, this is DFT running on my computer. The DFT here is calculating the single point total energy for a single hydrogen atom. And let me show you something cool. It's actually, you see this thing, text 3D, three-dimensional way of representing a single H atom sitting in the center of a box. GPAW like to do this thing because they know we, like Python programmers, like to use a lot of command lines. So they help us with no matter what system, no matter how complicated the system is, they're going to be doing this projection in 3D. So here you go. DFT is finished, and the total energy is, I save the total energy in E, variable E. So if I go print E like that, so that's the total energy for a single H atom, okay? The next thing is we want to calculate the total energy of H2, I mean the whole molecule. So it's just gonna be copy pasting this whole chunk of code here. and now it's doing the DFT for a H2 molecule. Let me show you. Yeah, there you go, H and H sitting inside in the center of this cell. So it's doing it now. And by the way, this is going to be a DFT optimization calculation, so it might take a few steps. Now, when I say steps, when you do a geometry optimization in DFT, there is the geometry or the atomic optimization steps and the SCF steps. The atomic optimization, the atoms move right a little bit until and then it runs the SCF calculation and then gets the forces on the atoms, too high forces, moves the atoms again, and then another SCF calculation. If this is not clear, please please ask questions as we go. If anything is not clear, I can just go over it. Okay, so it actually finished the calculation. 0.74 as a distance was enough to get very low, like sufficiently low forces on the atoms. And the energy here, E total here, is minus 6.64. Now, the atomization energy is given by this formula, E total minus 2 times E. Remember, E is the energy of an individual H atom. So if I do this, I'm gonna get that's minus 6.69, minus 6.7 is a bit too high. It's not correct, actually. To get the accurate atomization energy for a H atom, you need to incorporate the fact that a single H atom is, has a spin, obviously, because it has only one electron, right? So we have to make sure that this is incorporated in order to get the correct atomization energy, which is close to minus 4.5. So let's just demonstrate something here. If I want to get the the magnetic moment of that H variable, remember the H variable represents a H atom sitting in a box. So I go H, get magnetic moments. It's going to be doing the DFT calculation again because, yeah. Anyway, the magnetic moment is going to be 0. But, that doesn't make sense because a H atom has only one electron. And that one electron cannot have a magnetic moment of 0. We're forcing something illogical on that electron. So in order to fix this situation, we want to apply Hund's rule by setting Hund equals true in the GPAW object. And by the way, this is only valid. Here you go. So that's the magnetic moment, and it's 0 for the H atom. This is going to be only valid if you're doing a single atom calculation, obviously, because Hund's rule apply only for a single atom. So I'm going to be changing the calc object, the GPAW, object, and I'll create a new one with Hund equals true, and let's redo this calculation here. So when I redo this calculation, the value is going to be minus 0.87. You notice now the value is a negative number. Previously, when I calculated the total energy of the H atom, it was a positive number, positive 0.02 something, right? Positive as a total energy means that the system is not in a ground state. The system is unhappy. Negative is good. So here we have minus 0.8. So this means that it's actually a valid ground state. And when I calculate the total now, when I go ahead and do the calculation, E total minus 2 times E, which is the atomization energy. I just need to wait for this to finish. You know what? I'm not going to wait. I'm just going to take this value from here, and you can do this calculation on your own until it finishes. But in the interest of time, actually, it's going to finish now. Maybe we just wait. Any questions so far?
No questions so far on the chat, Sherif. Looks like
Beautiful.
you're answering everyone's possible questions very comprehensively.
Yeah, thanks. I hope so. Okay, so print E total minus 2 times E, and there you go. Well, minus 4.896. It's closer to minus 4.5, which is the correct numbers. That's minus 4.9. We're getting closer now. So to get, to actually hit it, we also want to use a good exchange correlation potential, and we're going to be using the PBE exchange correlation potential here. When you run this calculation on your own computer, you're going to get this value for the atomization energy, minus 4.488, blah, blah, which is very, very close to minus 4.5. So what we learn here is we created a new SAE object, the atoms object, to contain or to represent the structure of our system, which was a H2 molecule here. We calculated the atomization energy by creating two DFT calculations, one for an individual atom and the other for a molecule. And finally, we calculated the atomization energy by using that formula. So that's like, 101 DFT for a molecule kind of course. Okay, so the second part of this, the second tutorial is going to involve the structure of a carbon dioxide molecule. I'm going to go straight away into the code here. Okay, so in our case here, I want to determine or to optimize the structure of a CO2 molecule. Now, what I mean by that is I want to know CO2, what is the distance between that O and the C in the center, and that C and the O on the other side. So you have O, C, O, right? So what is this distance and what is that distance? Can we try 1? So like 1 angstrom here and 1 angstrom there. Can we try 2 or whatever? Well, I did this calculation earlier, and the value that GPAW is going to be happy with is 1.17103. But the thing is, I didn't want to, use a different value. Otherwise, we're going to have to wait a lot of time for this calculation to finish. So I just started from the calculation that will make GPAW happy, just from one single shot. So I'll show you how we can run this. So I'll, and of course, here GPAW x equals PBE, just like we did before. Set calculator, like we did before. And and this is a relaxation calculation. So quasi-Newton. I'm not sure if I discussed this. Oh, yeah. Actually, I didn't discuss the quasi-Newton before because I already started from relaxed H2 molecule. We didn't have to relax it. So in our case here, this is the quasi-Newton is one of the geometric optimization algorithms available in GPAW. There are a range of others that you can also check online on the GPAW website. And so let me just go step by step here. I'm gonna start a new terminal. Oh, actually, our terminal is already there. So I can just go delete this one and use this one. So copy paste. So A equals 10. That's the size of the supercell. Oh, sorry, of the cell. D equals 1.1 C 7. So that value here, we're using it to place the carbon and the 2 oxygens. You see the CO2. When I type CO2 here in this first string parameter for the atoms, the ASE atoms class knows that here I mean that I want 1 C and 2 O's. So you can just put the stoichiometric structure of your system, CO2, MOS2, and then this, the class is going to determine what the atoms in your system are. So we put CO2, comma positions equals, and there are 3, of course. We have the first one is for the carbon. We're going to put it in the center of the supercell. The second one is one of the oxygens. So it's A divided by 2 minus D. D here is that distance. And A divided by 2 plus D. And then the cell equals blah, blah, blah. And then we set the calculator. We create a GPAW calculator and set it to be the calculator for this calculation by CO2 dot set calculator. So remember that set calculator is a method in the atoms class. Okay, it's not a method in the GPAW class. It's in the atoms class. This method in the atoms class assigns a GPAW object as the calculator for the present atoms object. And then we're gonna create a relaxation calculation. So I'm creating the quasi-Newton relaxation object here, putting it in relax variable, and I'm passing the atoms. Now the atoms object remembers everything about what our system remembers the structure, and it also remembers the calculator, which is a GPAW calculator. So relax equals quasi-Newton, CO2, and then paste, and then relax the run, Fmax equals, now what this says, it says run the calculation until the maximum, until the forces on the atoms are less than 0.05 volt EV per angstrom. So this is the force tolerance in the calculation. Let me just check what I've done here. I think I just need to.
Sherif, just while you're
Yeah.
looking at that, we've got a question from Braden Kelly in the chat, and I think
Sure.
it might relate to something that's being done right now. And I wanted to
Yeah,
jump in and read that out in case we needed to clarify something.
Of course, please.
Braden says, what exchange correlation functional was used by default in GPAW?
Actually, to be completely honest, I forgot. I think it's the LDA, but I totally forgot. So I'll need to check that. It's somewhere on the website, but I promise you, I'm gonna be. I'll find it out, and maybe I'll put it in. You know what? I'll put it in these code files on my GitHub page.
Great.
Yeah.
Thanks.
Sorry, yeah, no worries. So yeah, it's stuff that you just forget. I think it was LDA. Okay, so here I'm gonna be just second. Sorry about that. I think after I get these here. Oh, okay, it's doing one SCF calculation, and after that is finished, it's gonna do it will run the relaxation, and after it runs the relaxation, I'm asking it to get the distance between the atom index 0, which is the carbon, and atom index 1, which is the oxygen, and that will be the correct distance. Okay, so that is the CO2 calculation going. I'm not sure if it's going to be a great idea for me to wait until this finishes. It's going to take a little bit of time. So I will just interrupt this calculation here. You guys can go ahead and test it yourself. I'm just kind of pasting it into your Python terminal. By the way, if there's any trouble setting up GPAW, I'm more than happy, just comment, just ask question here, or maybe later send me an email. Or email is sherif.abbas@mit.edu. Maybe I'll also add this email in the GitHub code pages if you have any questions. Okay, or you can just comment on the post, on the Twitter, the post that announced this tutorial. I mean, in any way convenient to you, you can deliver your question to me. If you have any issues setting it up, it's very easy to set up GPAW if you're using Windows, for Linux, or if you're using Mac. I've done it on all platforms, never found any issues. I'm now using Windows, by the way. Windows 10 has got the Ubuntu system, somehow emulated on top of Windows 10. And I have installed all sorts of DFT and MD packages using that system. So again, any issues, just let me know. Okay, so let's just go back now to the PowerPoint. So that's the CO2 structure, mainly the distance between the oxygen and the carbon. They're the same on both sides. So oxygen, carbon, carbon, oxygen, it's the same distance anyway. Okay, so these are two molecular calculations. Back to the exchange correlation that we just asked a few minutes ago. Let me just give a very, very quick overview if you're not very familiar with what exchange correlation is, because I didn't really go into that detail, but just to give it some fair coverage here in this tutorial, let me just quickly describe what it is. The purpose of DFT is to approximate the Schrodinger equation, right? Now, the Schrodinger equation is a very complicated equation. As I said, in the previous tutorial. Extremely difficult, so many degrees of freedom. So DFT dropped these degrees of freedom into just three numbers, like 3 degrees of freedom, X, Y, and Z of the electron density, which was amazing, right? But when it did this, imagine that the Schrodinger equation is this massive elephant, right? It's a huge elephant. DFT, because it dropped the complexity of the Schrodinger equation, it's pretty much like a little mouse in terms of its complexity compared to that massive elephant. It's a very small complexity compared to an absolutely terrible complexity, the elephant, but the difference in complexity was contained in what's like I would think of as a black box. The black box is called the exchange correlation potential or the exchange correlation energy, EXC here. So E, X is exchange, C is correlation. A big number of what DFT researchers do ever since the DFT was introduced to the world by Honenberg and Kuhn. A large amount of research and a large amount of time have been invested into finding good black boxes, like black boxes that can actually make this mouse as smart or as accurate as the elephant. Okay, there's a huge number of possible exchange correlation potentials with a lot of different types of physics and chemistry insights and even machine learning today. There is actually, and that's also a project I'm working on, this black box being a neural network, for example. Finding a good approximation to make this mouse as smart as this elephant, as I said, is one of the biggest research activities, and PVE, which was introduced in 1996 by a group of 3 star DFT people, is one of the very accurate exchange correlation potentials introduced for a very large number of systems, including molecules, including atoms, including solids, including even 2D materials. But PVE, even though it is really good for all those systems, it has its own problems. Like, for example, in 2D materials, it doesn't understand what the van der Waals interaction is between like 2 graphene sheets, for example. So let me just show you like how popular PVE exchange correlation is, the number of times it has been cited. Actually, this slide here is 1 year old. So I think this number, 112,000 citations for a single paper, man. Just one paper. You see these 3 guys here, Purdue, Burke, and Erznoff. I mean, come on. One paper, 112,000 citations 1 year ago. That's awesome, okay? So that's how popular PVE is. It's because actually, it's always like the baseline exchange correlation whenever you're doing any DFT calculation nowadays. We start with PVE as a baseline, and then we start adding more complexity to it, but it's acceptable as sort of a baseline. In the past, it was LDA, but then PVE just smashed it. Okay, so again, any questions? Just keep asking. Any criticism, any comments? More than happy in the chat window. Okay, so in the previous 2 demonstrations, they were molecules, but the next one is going to be periodic boundary conditions. And in periodic boundary conditions, you have your supercell, right? But the system looks at that supercell or that, you have your system, like your atoms together. You want GPAW to look at it as a repeated, like as a pattern. So instead of having just H2 molecules sitting in space, if you want a system that has H2 sitting in space, you're not considering this H2 to be, sitting next to another H2. You want it to be in space. So there is no periodicity along any of the directions. But if you want to represent, for example, diamond, the unit cell of diamond, diamond is a crystal, right? So the unit cell of diamond, which has 8 atoms, it's just 8 atoms, right? You want GPAW to look at it as, an infinite number of those 8 atoms repeated in all directions. So periodicity has 3 directions, the X and Y and the Z, right? If the system is periodic in 3 dimensions, like diamond, then it has, it's 3D periodic, right? In GPAW, you would set this by PBC equals 1, 1, 1. If the system is like graphene, 2-dimension periodicity, then it is 1, 1, 0 here in this list here. If the system is like a nanowire, then it is 1, 0, 0. And this PVC here is a setting that you put when you are instantiating the atom object. Sorry, the atoms object. Now in the next exercise, we're going to be doing a slab calculation. And it's a slab, so it is 2D periodic. It's a slab, right? So we're modeling a gas surface interaction. This gas is in yellow, the yellow sphere here, and then this is the surface. I'm putting these dotted lines or the dashed lines here because I want to represent just one unit cell. That's one unit cell that we're going to be building, repeated along the X and the Y dimension. So let's consider that this is the X. It's also going to be repeated along the Y, which is, so that's the X and that's the Y. So it's like a rectangle or like a square, repeated, like you create a tile of squares, infinitely many tiles of squares along the X and the Y axes. To build a system like this, all you need to do is just one square and then set the PVC to be 1, 1, 0. Luckily, when we're building a slab in GPAW, which is one of the really cool things about ASE, you really don't need to set anything explicitly. Atoms in ASE will understand that this is a slab, and therefore it will by default be periodic in 2 dimensions only. Okay, so let's move on to our slab calculation. That one. Again, it's also on the website, on the GitHub. And all of these, if you lose the link for any reason, you can just go back to the Exciton website, the tutorials, and you'll find all of these links there and all the materials there. And there is going to be also accompanying text with those code files on the Exciton website. Okay, how to build an FCC slab of platinum in ASE in just 2 lines of code. I know that, people have had to purchase software just to build slabs, you know that. Like you have a platinum, for example, and you want to build a slab of platinum, 110 or 111 surface of platinum. We're going to buy a materials studio, very hefty license cost with annual, renewal and all that sort of stuff. It's just 2 lines of code, man. Here, it just FCC. You create a new instance of FCC 111. It's already there, and there are a range of those methods for a range of other surfaces. So FCC 111, PT, which is platinum, already ASE already knows what platinum is. Size equals 1, 1, 3. Now, what does that mean? The size of the slab that you want to build is 1 unit cell along the x-axis, 1 unit cell along the y-axis, and 3 layers along the z-axis. So that's a 3-layer slab, 3 layers of PT atoms slab. And then put 10 angstroms of vacuum between every slab so that we can model, it's not periodic along the z-axis. We just want 10 angstroms of vacuum so that, if the vacuum is small, we're going to have trouble. We just want as much vacuum as possible above the surface. And the axis where the vacuum is going to be added equals 2. The axes are 0, x, 1, y, 2, z. So the vacuum is going to be along the z-axis, right? That's it. Slab is created. Let me actually show you what's going to happen now. So I'm going to just copy paste this stuff here. And then slab.write sif. Whoa, just written this sif file for the slab. And I'm going to be using the Vista software in order to visualize these files, the sif files. So I'm opening it now here, and there you go. Boom. So this is our slab. It has added 10 angstroms and 10 angstroms on both sides. And yeah, that's our 3-layer platinum slab. Okay, next thing is so we have 2 steps now to calculate the adsorption. And remember, this is for calculating the adsorption energy of a hydrogen atom on a platinum surface. We'll be doing the smallest calculation possible, and that's why the result would not be really accurate, but it's, you know, I'll tell you what to do to make it more accurate. So the first thing to do for a slab calculation is to calculate the energy, or to actually optimize the slab structure. This slab structure here is not optimized. You still need to optimize it. It comes as is from the bulk structure of platinum. Okay, so to optimize a slab, remember, if you have a slab like that, right, and you want this slab to emulate a bulk surface, like you want to make this slab to pretend that it is actually sitting on a large number of platinum layers, one thing to do, and we always do in slab calculation, is to freeze the bottom atoms. Now, how many atoms do you want to freeze? For now, just for simplicity, I'm freezing those 2. Okay, so let's go back here. So now, which 2 do I want to freeze, and how do I freeze? To freeze atoms in GPAW, and atoms actually in ASE, you need to call the fixed atoms class. Fixed atoms is one of many geometry constraints class supported in ASE. It has an amazingly large number of constraints available. That's obviously the simplest. It just freezes each atom along all axes, the 3D, the X, Y, and Z axes. And what you need to pass to fixed atoms is the indices, a list of the atom indices, right? So what atom indices do we want? Let's just go back and call get positions from slab that we used previously. So we have 3 atomic positions here, this one, that one, and that one. The bottom one is at 10 angstroms, remember, because it added 10 vacuum below the layer and 10 above. So the first atom in the slab is at 10. So 10, and then there is 12, and then there's 14, right? So I want to freeze the bottom 2, the one at 10 and the one at 12. So that's index 0, index 1, right? So when I call the fixed atoms, I'm going to pass 0 and 1 as indices. And then I need to set constraints with that fixed atoms object. So copy that stuff and then paste. Next thing is I'm going to be doing the constructing the GPAW object. And here I want to show you a few more features in GPAW, the GPAW class that supports superset calculations. K-points. So here is how you can provide the gamma-centered K-mesh. 2, 2, 1 is like a 2 by 2 by 1 K-points mesh. And you can also set the spin polarization to be true. By default, it's false. And so you have to explicitly set it to true. We don't need spin polarization here in this calculation to be true, but I'm just showing it. I'm putting this here just for them to show you that this is how you can do it. And of course, when you go to the GPAW website, you'll find a large number of different, parameters that are supported, or arguments that are supported in the GPAW object. So first you create the GPAW object, and then you set the calculator to be whatever that is. So slab.set calculator, which is this object. And then again, we set up our relaxation like we did before in the CO2 calculation. So what I'll do here, I'm gonna get these. Now, one thing I wanted to tell you about these lines of code. This calculation will take a bit of time, maybe 2 or 3 minutes. I don't want you to keep waiting here for this that long. So I'm just showing you here that the total energy for that slab after optimization is minus 20.5 EV. And after this calculation finished, I also wrote the optimized slab. So let me show you something. So here it is, PT optimized. That's the optimized slab structure here. So I'm gonna just do this here, and Okay, do you notice something? Optimize. Sorry, not that. No, I think it's not that one. Okay, I think I wrote the wrong files. Oh, yeah, okay. So these were previously written. Sorry, the new ones were overwritten by mistake. So this is the original. This is the original structure, and then after optimization, I got that. Do you notice that the top PT atom went down a little bit, but the bottom two PT atoms did not move at all. And that's because of the constraint that I have applied on, I fixed the positions of those two atoms, right? Okay, this is gonna keep running, so let's just ignore it for a bit. The next calculation to do is to add an adsorbate. Now, there is actually a method in HSE called adsorbate. It takes the slab structure. Remember that this slab structure is the one that was optimized already. So after we optimize the slab, we call adsorbate is kind of add the H atom, and we can put whatever we want here. We can add a graphene layer on a slab using adsorbate, and then 1.7 here. This is the distance between that system, which is the H atom, and the slab. And then I can also specify for this slab that I want to put the H atom on an on-top position. I mean that the H atom is going to be straight above a PT atom. So once we do this, let me show you what the result is going to look like. Here it is. So here's the H atom added on top of a PT of the optimized slab structure. Now, once we're done with this, the next step is we do the calculation again. So set calculator, calc PBE. Remember, I don't need to create a new GPAW object because I already have one here, which is this one. It's also always important, of course, to use the same DFT settings for all of your systems or the subsystems in a surface, gas surface adsorption calculation. So we're using the same calculator here for the slab. And also, by the way, this is the same settings that we used, apart from the K points, same settings we used for the H2 molecule. So we can just use the value of the total energy of the H2 molecule in this calculation, as I'll show you later. So here we calculate the slab, including the H, and after this calculation finishes, total energy is going to be minus 24.22, blah, blah, blah. And the system, the relaxed or the optimized system is going to look like this. Actually, not this one, this one. So this is the H atom on top of the PT. It starts from here and it goes up there. Okay. Now, one thing I wanted to point out, you can see that the calculation is still running. That's fair enough. It's a DFT calculation. It's not meant to finish in a second. If it's an MD calculation, it would. We don't have enough time, unfortunately, to go through molecular dynamics. But I promise we're going to have another session. We're going to cover that. But for now, it's just DFT, and DFT does take time, even for 4 atoms like we're doing now. That's actually 3 atoms still. But remember, it's a platinum. It has a lot of electrons, and that's one of the reasons why it is complicated. It's taking too much time. And also, it's a 2 by 2 by 1 K points. If it was just 1 by 1 by 1, like a gamma point, it would take much less time. But gamma point for slab with a metal is not a good idea. Actually, 2 by 2 by 1 K points that I have set here is still pretty bad for platinum. The adsorption energy that I got when I did this calculation is minus 1.47, blah, blah, blah. That's it. And that's the adsorption energy formula, by the way. The adsorption energy is equal to the slab, including the hydrogen, total energy, which is the second DFT calculation here, minus the slab without the hydrogen, which was the first, the one in step 1, minus the H2 molecule energy divided by 2, which we obtained in the first code file, the basic calculations one, this one, the one where we did the hydrogen atomization energy. So I'm just using that value here, putting it here, divided by 2. Because typically when a hydrogen goes and attacks a platinum surface, it's a hydrogen molecule and then it splits, right? So we divide the total energy of a molecule by 2 to get the energy of a single H atom, and that's also how this formula is applied in the literature. So the absorption energy is minus 1.47. However, the correct value is minus 0.5 EV for a single H atom on platinum. But to get to that number, we need to have way more K points, like 2 by 2 by 1 is really far away from that. It should be at least maybe 8 by 8 by 1. Even more would be better because it's a metals. Metal surfaces normally require way more K points. Okay, so now that we're done with this calculation, yeah, actually that's all. I'm glad that we made it at the right time. We've got 5 minutes for questions. If you have any questions, you can ask either voice or actually I prefer that you ask on the chat. Otherwise, it's gonna be a mess. Yes, thank you all for attention.
Thank you very much, Sherif. That was great. Really, really interesting. I hope everyone enjoyed it. We've got a question from Braden in the chat.
Yeah.
He says, how is GPAW's speed compared to, say, VASP or quantum espresso? I'm interested in molecular crystals, so unit cells with up to hundreds of atoms. Can GPAW handle that many atoms?
Okay, I haven't tried GPAW for that many atoms. I have only tried GPAW for like systems with maybe half that number. It's close to the speed to VASP. If you use GPAW with plane waves, it's going to be close to VASP and close to quantum espresso. Because remember, even though GPAW is written in Python, it does all the linear algebra using BLAS and all the C or the Fortran-based linear algebra packages. So it doesn't, all the hard work is not actually done by Python. And that's why the speeds are not really, it doesn't really impact the speed much that it's written in Python versus VASP, for example. I mean, you can try and tell me. I'm actually curious to know. I'm using, I'm gonna be starting to use GPAW for an MD calculation that has thousands of atoms. I'm gonna also see how this works. We'll tweet about it at some point.
Great, looking forward to hearing how you go with that one, Sherif. And Braden,
Thanks.
if you try using it, then please let us know how you get on for that purpose.
Absolutely, yeah, absolutely, yes, we'll do.
Got a question from Gionu, who says, are these kind of steps we have followed today similar in VASP? I heard VASP is also very useful for DFT calculation.
Okay, that's a great question because I'm gonna be teaching VASP next tutorial and the one after. So 3rd of May, same time, same day. So Monday, 3rd of May, 11 a.m. of Melbourne, Sydney, Canberra time. I don't know what the time zone that you have, but that same time, next in 2 weeks, I'll be covering, it's gonna be 2 weeks, yeah. I'll be covering VASP and also the, let me just answer your question about whether they are similar. They're very different. VASP is a Fortran code, okay, Fortran DFT code. You feed in your inputs into VASP, like the system and the calculation parameters, using files that VASP has introduced just for that. So there is a K-points file to determine your K-points. There is an in-car file for all the DFT calculation parameters. Okay, like what do we put in GPAW? No, there's a file for that with tags. Tag name equals some value. Tag name equals some value. That's a separate file. And the pseudo potentials, you put them in a potcar file, so a separate file. And the system itself in what's called a postcar file, which is also, so 4 files. That's VASP, right? GPAW, no, it's way simpler as you've seen today. Just few lines of code, you can establish a whole set of calculations. But I have to say, VASP is pretty much like a standard in DFT. It's complicated to deal with, but it's also very, very accurate, very well served by the community. The VASP community has been used for ages, has been cited in science and nature journals. It's always like the let's say the standard or the benchmark. I would use VASP for a calculation as a starting point, just to make sure that everything is in the right place, and then compare my GPAW against VASP. If I'm happy with the comparison, I then continue with my GPAW, to be completely honest, because GPAW is more recent than VASP. Hasn't been tried for that, for a lot of, it has been tried for so many systems. It's proven to be accurate, benchmark and all that, but VASP has been tried for a lot more systems. That's why.
Great, thanks, Sherif. That sounds a really interesting contrast between those two, and I'm sure people will be very interested to find out about VASP in the next couple of sessions.
Sure.
So we also have a question from Paul. He says, do your DFT calculations include van der Waals interactions when minimizing the energy of the system?
You can definitely, sorry.
Yeah, that's two-part question. So do you want to answer that one first, and I'll add the second part of the question in after that?
Yeah, I'll answer that one. You can add whatever van der Waals correction in GPAW. So GPAW also comes with, so GPAW has a lot of different exchange correlation potentials. It also lets you set your van der Waals. Like in VASP, you put IVDW equals a number in your in-car. There's also a way to do it in GPAW.
Great, thank you. And the second part of the question is, for an adsorbate system, can you predict where the surface reconstruction occurs?
Absolutely. You just do the minimization, like you optimize the surface. So you build the surface large, like wide enough for a reconstruction to occur, and then you start the optimization. And by the way, you can do simple DFT stuff on your PC, but when the system becomes bigger, you cannot do it on your PC. You need to submit an MPI job on a supercomputer to do that. So it's just like we do in VASP and Siesta and Octopus and all these DFT codes. GPAW is also a parallel programming platform, so it can handle large calculations in parallel as well on a supercomputer.
Cool. Thanks very much. Hopefully that answers. Yeah, Paul says thanks. So that looks like it's answered his question.
Cool.
Got a couple more questions coming in. Another one from Gionu, who says, I remember that you are trying to solve DFT with neural network, which looks very interesting. Could you introduce your objectives a little bit?
Yeah, okay. There's going to be a session about my progress in doing this, but let me just give a little overview. Why do we do DFT to start with? We do DFT to calculate the total energy for a given system. Let's say you have like carbon dioxide, so OCO. We want to find out, given this atomic configuration, what is the total energy for the system. That's the main thing about, the key outcome from DFT. You can also find out a lot of other things using wave functions, right, in DFT, such as the HOMO-LUMO gap, the energy eigenvalues in general, excited states, and all sort of things, right? But one important quantity that we use DFT for is the total energy, because based on the total energy, you can optimize the structure. The forces that we get between atoms are derived from the differential of the total energy, right? So if you have a way to find the total energy for a system, then you can also find out the forces between the atoms in that system if you're able to predict the total energy for that system where the atoms are in many different positions, i.e. you can find a smooth representation for the total energy as a function of the atomic positions. Neural networks have previously been used to find the total energy for a silicon supercell. There's a PRL paper about that. It's like, I think 2013 or something. And they represented their supercell of silicon based on a set of features. And they were able to correlate between the total energy of the silicon crystal and those descriptors using, I think, using a machine learning model, which I think it was in neural networks. Now, my objective is to expand on this. I'm using a larger range of descriptors for a larger range of systems, not just silicon. And I'm now trying to obtain a correlation between using a neural network model and a couple of other models, correlation between the descriptors of those systems and the total energy. Total energies here are obtained using VASP. So I get the total energy. First, I start with a system, mess around the atomic positions randomly, or sorry, not randomly, using molecular dynamics. So I use GPAW MD to generate a data set. And then for each one of those snapshots, I do the DFT calculation using VASP. I get the number, which is total energy. And then I try to reproduce those numbers or predict those numbers using a machine learning model. So, so far the R-squared, or the prediction accuracy, the regression prediction accuracy has been really, really cool, like 0.8 something. And it just keeps improving as we, over the weeks. Hopefully I'll be having a draft about this work submitted soon. Yeah, so that's just in short what's been happening in this respect.
Great, that's fascinating.
Thanks.
Good luck with getting the draft of that paper finalized.
Thanks. Yeah, thank you.
And last question perhaps for today, I think, is from Braden, who says, can GPAW do GPUs?
Oh yeah, I think so, yes, but I need to check again. Yeah, you know what? I noted down the previous question. I'm gonna note that one down, and I'm going to answer it on the code files.
Right.
So in the so the first one, the basic calculations _1, I'll put an answer there. It's on the website. I remember seeing it, but I don't want to give a straightaway answer. Yeah.
Okay, great. So if you can keep your eye on the website, Braden, then hopefully we'll be able to put that answer up for you definitively a bit later on.
Yep.
Great. Well, that's all the questions we've got, and we're getting on for 12 now. So it's wonderful that so many people have been really, really interested and engaged in what Sherif's been talking about today. And I'd like to thank everyone for joining us, and to thank you again, Sherif, for taking the time to explain this to everyone today.
All right, thanks a lot, Ian, for organizing this and making this all happen. And thanks everyone for your attention.
Great. Thank you, everyone. We'll hopefully catch some of you here again in 2 weeks for the next session.
Yep. Sure.